Namaskaram. Welcome to my channel, Chemistry in a Nutshell. Today I'm going to discuss about, I'm still continuing with the solid state. Today I'm going to discuss about the relationship between the radius of an atom and edge length. Of a unit cell. So what we are going to do is we are going to find out a relationship between the different types of unit cells, atom, and the radius of the atom and the edge length. So what do I mean by that? Suppose, say for example, you have since we are taking solids, we know that in solids the atoms, say for example this particular circle represents an atom, actually it's a sphere. They are closely packed. Remember, I was continuously stressing on this word, closely packed. So when I'm telling closely packed, there is hardly any space between these two atoms. And if this is the center or the nucleus of the atom, this distance is r, or this distance is r. That means from here to here the distance is r, from here to here the distance is r. So that's the radius of this particular atom. And when I'm talking about the edge length, I'm talking about unit cells which are cubic in nature. The other different forms which we have learned prior to this particular video, you will not get questions related to that. You will only get questions which are related to cubic unit cells. And it's very easy to find out the relationship between the radius of the atom and the edge length in a cubic unit cell. So cubic unit cell, I believe you remember, where the length, breadth and height are all equal, remember? The length, breadth and height are all equal, and even the angles. So alpha is equal to beta equal to gamma is 90 degree. I believe you remember. And similarly, the distances A, B and C, they are all equal. Now when I'm talking about edge length, these are the edges. This is an edge, this is an edge, this is an edge, this is an edge. So these are the edges. So this edge, if we take it as A, where A is this, that's the edge length, and we are supposed to find the relationship between this edge length and the radius of the atom, that is R. So we are going to find out a relationship between radius and A, R and A. This is what we are going to do. So first, what we are going to do is, we are going to take number one, simple cubic unit cell. So we are going to find out the relationship between the radius of an atom and edge length for a simple cubic unit cell. Now, I believe you remember what's a simple or primitive cubic unit cell. We have taken, while explaining, I had given you the example using a cubic unit cell. So in cubic unit cell, all the atoms are partially inserted on the corners of this particular cube. So remember, let me draw it. So we are taking a simple cubic unit cell, and here at the corners we have the atoms. Each of these dots represent the nucleus of an atom, say. For simplicity, we'll take only the top face of this particular cube. For simplicity, nothing else. You can take either of this side, either of the faces. It doesn't matter. Here it is easier to explain. That is why I'm taking the top edge. We are going to take this particular edge, and since this is a cubic unit cell, we know that the edge length is always same. So if this is A, this is A, this is A, so each of this edge length is A because it's a cubic unit cell. So here I have taken the length as A of the edge. So this is the length which I have taken as A. And what I'm going to do is I'm going to draw the entire atom out here. Say using dotted lines, I'm drawing the atom, more or less I'm trying to draw a circle, and out here also we have a atom. They are closely packed, they are touching each other. You can imagine this to be touching each other. So here, what is the distance? What is the radius of this atom R, and what is the radius of this atom R? So from the figure, it's very clear that twice of R is equal to A. That is twice the radius of the atoms is equal to the edge length. Or we can tell R is equal to A by 2. Simple, isn't it? So this is the first relation which we get. So now we are going to learn the second type of unit cell, cubic unit cell. So that is face-centered cubic unit cell. So this is what we are going to learn in the second situation. So here what we are going to do is, first of all, let me draw the cubic unit cell. Remember, in the face-centered cubic unit cell, we have atoms on the 6 faces of this particular cube. Along with the atoms at the corners, we also have atoms at the faces. So we are going to find out a relationship between the edge length and the atom at the face. So we have the atoms at the corners as usual. This is just like the simple cubic unit cell. Along with that, we have atoms at the different faces. So there are 6 faces. This is at the top face, this is at the side face, this is at the other side face, this is at the bottom, this is at the front, this is at the front, and this is behind. So total we have 6. Now for convenience, we are taking the top face only. So here you can imagine this to be an atom. I'm drawing it in the form of a dotted line, and remember, the atom which is at the face, it is always at the center. It is always at the center of the face. It is not anywhere in any direction. It's always at the center. So if you can imagine there to be a diagonal over here, so the nucleus of the atom which is on the face, it will be exactly at the bisection of this particular diagonal. So here you have the next atom, and here you have the next atom. And here the length of the edge taken as A, obviously, just like before. And we can even take this. Now, okay, what we do is we make it flat. It is easier for us to understand. This particular, top face, I am drawing it in 2 dimension. So here we have a square, and here are the 4, atoms are the 4 corners. And here is the diagonal. And at the bisection of the diagonal, we have the atom which is at the center. Now we are going to draw the radius of the entire circle representing the entire atom in 2D space. Here we have the atom which is on the face, and here again we have the atom which is at the corner. So here If you imagine this particular radius is r, this is also r, this is also r, this is also r. And here the edge length is taken as a. Here too we have taken the edge length as a. So this particular angle is what? It's 90 degree, because in a cubic unit cell alpha, beta and gamma is always 90 degree. So here if it is 90 degree, we can use the Pythagoras theorem to find the relationship between the edge length and the radius. So what do we get? So now we are going to find out the relationship. Since this is 90 degree, we can simply use the Pythagoras theorem to find the relationship between this particular hypotenuse and the two sides. That is a square plus a square equal to 4r whole square. So what do we get? 2a square or 2a square equal to 16r square, or a square equal to 8r square, or r square equal to a square by 8, or r is equal to a by 2 root 2. Now multiplying root 2 with both numerator and denominator, what do we get? We get r is equal to a root 2 divided by 4. So this is the second relationship between the radius and the edge length, radius of the atom and the edge length in a cubic unit cell, which is of face-centered type. Now we are going to learn the third one, that is body-centered type. Now what we are going to learn about the body-centered cubic unit cell. So the third one is body-centered cubic unit cell. I believe you remember, in a body-centered cubic unit cell, we have an entire atom, a full atom inside the unit cell. So that means the entire atom is inserted into this particular cube. So let me draw this first, a cubic unit cell. It's very simple, don't worry at all, except your visualization is required. That's good enough. And this particular part is very important because there are a lot of mathematical problems which are related to it, which I'm going to talk about it definitely. So here we have a cube, and of course we have the atoms at the corners, no doubt regarding it, that still holds true. And we have an atom which is at the center, of the entire cube. Now the atom which is at the center, which is inside the body, the atom which is inside the body of the cubic unit cell, it is at the center of the cube. So when I tell at the center of the cube, what do I mean? It is actually placed on the body diagonal of the cubic unit cell. Now what do I mean by body diagonal of a cube? Body diagonal means, if you draw a line that joins this particular point with the point which is opposite to it but at the lower end, that particular imaginary line may be considered to be the body diagonal. And at the center of this particular, so here you can imagine it is somewhere here. I'm drawing it using a dotted line. So this is a body diagonal, and at the center of this, say this is the center, we have the atom which is inside the body of the cube. So what do I mean by body diagonal? Let me demonstrate this. I've taken a cuboid rather than a cube. It doesn't matter, you will still be able to understand. If I draw a line from this particular edge, the edge which is behind, that is which is in front of me, which is at the back, with this particular point, that is the point which is opposite to it, diagonally opposite to it, and at the lower end, if I draw a line And if I take the bisection or the central portion of it, what we get is the middle portion of the body diagonal. Out there, the nucleus of the atom, which is inside the body of the cubic unit cell, is placed. So now, how do we find it? So now, let me draw the atoms, the radius of the atoms. So this is one atom whose radius is r, and here once again we have one more atom whose radius is r, and out here also we have an r, and again we have an r. So in this particular diagonal there are 4 r, you can see it, one r from here, another here, another here, another here. So we have 4 r's. And what are the different edges? So of course, since it's a cube, every edge is of length a. So this is a, obviously. This is even a. Even this is a. So simple mathematics. In a body diagonal, there are all these sides. The square of these sides is equal to the square of the sum of this plus this plus this, because it takes, so mathematically 4r whole square is equal to this a square plus a square plus a square. Simple. This is simple mathematics. This, the length of the entire body diagonal is equal to this plus this plus this. So how much do we get? 16r square equal to 3a square. So r square equal to 3a square by 16. So here what we get? R is equal to a root 3 by 4. So that's the relationship between the radius of the atom and the edge length in a body-centered cubic unit cell. That's it. Isn't it very simple? Now what I'm going to do is, I'm going to write the entire summary of this, that is in the form of a table. Why? What I'm going to do is, now I'm going to summarize this entire thing. I'll write it in the form of a table, and you need to learn this by heart, because this is what we require for learning how to perform calculations which are related to packing efficiency, which we are going to see next. So I'm going to summarize the entire thing. This is what you have to learn by heart, because we require it in the next part of this particular lesson, that is calculation of packing efficiency. So we are going to write the relationship between radius of an atom and edge length. So first of all, we'll write the crystal system. That is, what type of unit cell we have used over here. Then we are going to write the rank. Remember, rank represents the number of atoms per unit cell. And here we are going to write the relationship between the radius of an atom and the edge length in the unit cell. So first one is simple or primitive cubic unit cell. And remember, in a cubic unit cell, it is always at the corners. So the rank is 1. We have already studied about this before. And the relationship was radius equal to a by 2, where a is the edge length and r is the radius of an atom. Or we can write it in with respect to a is equal to twice the radius. Now we are going to write about the face-centered cubic unit cell. Face-centered cubic unit cell, just recalling it, there are atoms at the corners, obviously. Along with that, we have atoms on the different faces of the cubic unit cell. So here, the rank is 4. We have already studied this before. And the relationship is radius is equal to a root 2 by 4, or with respect to a is equal to 4r by root 2. And finally, we are going to learn about the body-centered cubic unit cell. The rank is 2, obviously, and radius is a root 3 by 4. Very simple to remember. Or with respect to a is equal to 4r by root 3. Now students, please remember, you need to learn this table by heart, because this is the basis of all the calculations which we are going to learn in the next part of this particular lesson. Thank you. Namaskar.